In this section, we'll take a look at one of the possible problems when dealing with data allocation. In past modules, we've discussed how the data represented by an RDD is actually partitioned across any number of workers. In many cases, this distribution of partitioned data works out pretty well to complete the job in the most efficient manner. However, there are cases where the partitioning can work against you. These skews can be from the data not being distributed optimally, or can be from some worker machines working slower than others. In this section, we'll take a look at one of the cases that could lead to data skew, how to detect it, and then fix it. To be able to display this simply and locally, I've added some code to emulate the situation. First, we'll load our RDD with a lot of data, partitioning it into 10,000 chunks. This is a bit contrived to make the point simply. However, you can imagine loading a heavy dataset that needs a large number of partitions. Now, somewhere down the line of execution, a filter is executed which drastically reduces the dataset. And then some more transformations are done before finally performing an action. Let's see what happens. Our giant dataset has been transformed into a teeny tiny one in comparison. So, it did indeed work. However, was it performant? Well, we can see that it ran in two chunks, with both running against 10,000 partitions, totaling 13 seconds in the first part and another 20 seconds in the second part. Looking at the collect, and then its sort by, which occurred after the filtering, we can see that there are a lot of tasks that ran in no time, because they were empty. This overhead cost us just about the whole of the second portion. 20 seconds. So, back at the shell, I've added a call to the coalesce method right after filter. What this will do is repartition the RDD down to the specified number, reducing the unnecessary overhead of empty partitions for future methods. And, as an aside, there is a method more aptly named repartition. However, it should only be used if you're increasing your partition count. The reason is that coalesce is only for partition reduction. And because of that, it'll avoid a full reshuffling of the data, opting to keep any data already on the remaining partitions. Now, the other parameter set is the shuffle flag. This makes it act like a repartition, as it signifies that this should result in a shuffle, thus splitting the job at that point. When you have such a large reduction, this denotation becomes important, as without it, all items in that stage will drop their partitioning, even those that occurred before the filtering, which might not be what you want. When dealing with data skew, these are just some of the things that you need to keep in the back of your mind. Running the code, we can see that we still get the same results. But is it any more performant? Here, notice that while the first part ran for 10,000 partitions, which is what we wanted, as that segment of code still worked against the pre-filtered dataset. And it ran in about the same amount of time as before. However, its second chunk only took a few seconds. We can go to sort by and see that the coalesce was the heavy lifter, with the sorting being against the pared down dataset. So, going back and comparing the two runs, we can see that our coalesce saved us a magnitude of time. And as you scale your data and computations, the savings could become even more noticeable. Now, before closing, it should be noted that using data frames with predicate pushdown can alleviate this problem. However, being aware of the symptoms, a bunch of very short tasks, and how to resolve it, should it still occur due to the way that your code might be written, well, that could save you a lot of time in debugging and processing.